Hey everybody! Today we will be taking a look at the basics of process control and safety systems and how they relate to a HAZOP. Specifically, we will be looking at what a basic process control system is, as well as what a safety instrumented system is and how they work together for process control. Let's join our operator Bob at the facility giving a walkthrough to a new trainee.
This is the Basic Process Control System, or BPCS. It is the main computing system for the site. It receives information about the process, including pressure, temperature, flow, and level from transmitters on the system, and outputs signals to manipulate the position of controlled valves in the process to ensure the system continues to operate at the desired operating conditions.
So this computer is controlling everything in the facility?
Pretty much. Let's take a look at this system as an example. This two-phase feed of liquid and gas is supplied to V1, which separates the liquid and gas, with the gas stream leaving out of the top of the vessel and liquids out of the bottom. Now, let's look at the level control loop on V1. Here the level indicating transmitter, LIT1, is sensing the level of the vessel, and then transmitting that signal to LC1, the level controlling function on the BPCS. Based on the signal received, LC1 will send a signal to the level control valve, LV1, to open or close as needed. If the level increases and is higher than the desired set point of the controller, then LC1 will send a signal which will cause LV1 to open more, allowing more liquid to flow out of V1. If the level decreases and is lower than the desired set point of the controller, then LC1 will send a signal which will cause LV1 to close more to restrict liquid flow out of the vessel.
But what happens if the BPCS controls malfunction?
A safety instrumented system, or SIS, is an independent computing system from the BPCS, which monitors the system for potentially hazardous operating conditions. If the SIS senses a hazardous condition, it will send a signal to a final element, typically an actuated emergency shutdown valve, or ESDV, to isolate or shut down the system. This action is called a safety instrumented function, or SIF, which may have an associated safety integrity level, or SIL rating, which quantifies how reliable the SIF is. The SIS should be independent from the BPCS, with separate transmitters, final elements, and an independent logic solver. Its job is to bring the process to a safe state in the event of a failure of the BPCS. To do this effectively, the SIS cannot share any potential common cause failures with the BPCS that would jeopardize its ability to act. An example of this would be using the same level bridle in a vessel for both the BPCS and SIS transmitters. If the bridle is plugged, control of both systems would fail. The requirements for safety instrumented systems are further detailed in International Standard IEC 61511. This is the standard for safety instrumented systems for the process industry sector.
A majority of the process control operations are handled by the BPCS. The SIS acts as a second line of defense in the event of a failure on the BPCS or an upset condition that the BPCS cannot control on its own.
So most of the time the SIS isn't doing anything?
Not exactly. The SIS is constantly receiving signals from the process to ensure it is operating safely. Looking back at the vessel, the level transmitter LIT2 is sensing liquid level in the vessel and transmitting a signal to the level controller LC2, the level controlling function on the SIS. During normal operations, the BPCS will be controlling the level, and there is no need for the SIS to act. If the BPCS controls fail and level in the vessel begins to increase, when the liquid level gets too high and reaches the set point of the level alarm, high, or LAHH of LIT2, the controller LC2 will alarm and send a signal to close ESDV1. This will shut down the process by cutting V1 off from the upstream liquid source, which will prevent the level in the vessel from increasing any further.
Why are we so worried about the level that we need to shut down if it's a little higher than normal?
It is important to keep the level in V1 near the set point of LC1. If the level in the vessel gets too high, there's a potential to carry liquids over to the compressor downstream on the gas system. This could cause a catastrophic failure in the compressor.
The BPCS is the primary control system for any modern process. Without it, processes would rely on local controls and operators manually operating valves to manipulate and control the operating conditions. A BPCS makes process control safer and more efficient. However, some processes are not inherently hazardous enough to justify having an SIS, or they were built before having an SIS at a facility was common. Some processes can mitigate hazards by using other means, including pressure safety valves, locally controlled shutdowns, or shutdowns wired through the BPCS. The decision to have an SIS at a new facility should be made early in the design process, as it can add significant cost. The process hazard analysis, typically a HAZOP and LOPA, would identify the specific SIFs required for the process, as well as what the associated SIL rating required for each SIF is. Let's jump in with our HAZOP team as they conduct a LOPA to identify how they would determine the reliability of the SIF required for the vessel V1 we have been looking at.
All right, we have identified that the level control valve LV1 failing closed would cause liquid to carry over from the separator V1 to the compressor downstream. This would result in a potential catastrophic rod load failure of the compressor, causing a significant loss of containment of vapor, with the possibility of a vapor cloud explosion and potential fatality. Let's jump into the LOPA. Based on Center for Chemical Process Safety guidelines, the typical failure rate of a control valve is once in 10 years. Does this seem reasonable for this service?
I've dealt with similar separators at other sites. I've seen a few level control valves stick closed in my time. I think that sounds reasonable.
Good. How often do we expect personnel to be in the area?
This will not be a highly trafficked area of the facility. However, I think that it's unlikely we could say that someone will be in the area less than 10% of the time, just based on operator presence.
All right, then we can't take credit for a conditional modifier.
There is a high-level shutdown on the suction scrubber of the compressor wired to the compressor's logic solver. If any liquids reach the scrubber, it will trip the compressor before any damage can occur.
Excellent. We can say that safeguard is at least 90% reliable, or that it has a probability of failure on demand of less than 10%.
We also have the high-level shutdown LAHH2 to close ESDV1. We haven't completed the detailed design of that system yet. However, the facility SIS will be capable of supporting SIL-3 systems.
Unless there's another layer of protection, it will need to be at least 99% reliable, or have a probability of failure on demand of less than 1%, which means it will need to be a SIL-2 rated system.
That will add some cost to the project. Luckily, we identified it early enough that it shouldn't be too much of a setback.
It is important to understand the process control systems involved in a design when taking credit for safeguards in a HAZOP. These systems are used to maintain safe operating conditions by ensuring the process functions as designed, making the process safer for operators working in the facility and preventing potential damage to equipment. Thanks for watching. If you enjoyed this video, please check out our online Process Hazard Analysis certification course. The course includes a year of email support and covers topics including HAZOP, LOPA, and SIL.